Now the next part of rate of reaction actually comes from interpreting data from experiments. Okay, so as we mentioned before, the gradient of the graph represents the rate of reaction. The steeper the gradient, the faster the rate of reaction. Now this is true, be it in a positive gradient or a negative gradient. When the gradient becomes zero or totally flat, the reaction has stopped. Okay, so if you look at this example, the reaction between zinc carbonate and excess hydrochloric acid, carbon dioxide gas is produced. So let me write down the equation. Zinc carbonate insoluble, add to acid, aqueous state, gives me zinc chloride soluble, water, and carbon dioxide gas. So they are saying that this is the gas that's produced. Okay, so we determine the rate of reaction by measuring the volume of gas produced over a fixed interval of time. So you can see that it's always important, where did the graph start? It should start at 0, because at the start of the reaction, there's no carbon dioxide. It is produced over time, and you can see that there's 3 points here. Point A, and time equals to 0. This is when the gradient is the steepest. Thus, the rate of reaction is the fastest at this point. How do we explain this? Now, at the start of the experiment, the concentration of the acid is the highest. Okay, that's because nothing has reacted yet, so the concentration of your reacting particles is actually at the highest. Okay, so following that, you can see that how I explain actually links back to this part on concentration of reactants. So when you talk about concentration of reactant is the highest, that means it has the most reacting particles per unit volume. This means that the frequency of effective collision is the highest, and hence the rate of reaction is the fastest. Okay, so you see here. So the number of reacting particles per unit volume is highest. So frequency of effective collision highest, rate of reaction fastest. So you can see how I mirror the steps to explaining how concentration results in higher rate of reaction. Now at point B, so point A, this is your gradient. At point B, can you see that the gradient is now somewhat less steep? Okay, maybe I draw it a bit more obviously. Okay, so you can see that the gradient has now become less steep or gentler. Gentler. This means that the reaction is getting slower. How come ne? As the reaction progresses, we see that the concentration decreases. Of what? Of the acid decreases. Why? Concentration should only be used for things in aqueous state. So that's why we specify that it's hydrochloric acid. Okay, the number of reacting particles per unit volume decreases. Hence, frequency of effective collision decrease, rate of reaction slower. Again, we are answering in the same 4 steps. At point C, which is at this point, okay, we see that the gradient starts to become 0. The rate of reaction is 0. So again, gradient tells me the rate. This tells me that reaction has stopped. Now, when do reactions stop? They stop when the limiting reagent is fully used up. So going back to the question, which is your limiting reagent? in this case, they didn't give you any values to calculate, but actually what they did was even better. They tell you that HCl is in excess. Hence, this must be your limiting reagent. So here is zinc carbonate, which is your limiting reagent, is fully used up. This shows that the reaction has stopped. Now, another way we can determine the rate of reaction is again to measure the mass of the reacting mixture over a fixed interval of time. So instead of measuring the volume of gas, we measure the decrease in mass because of the gas evolve. Okay, so let me just write down. The mass should decrease as gas is produced and leaves the reaction mixture. So again, we have 3 points. If you can draw the gradient at each of these points. You will see that at point A, again, when time equals to 0, this is where the gradient is the steepest, and when rate of reaction is the fastest. We explain in the same way: concentration, highest; reacting particles per unit volume, highest; frequency of effective collision, highest; rate of reaction, fastest. Okay, at point B, the gradient is less steep or gentler than point A. This shows that rate has slowed down. How to explain? Again, because some acid has been used up, the concentration of acid has decreased. Number of reacting particles per unit volume decrease. Frequency of effective collision decrease. Rate of reaction slower. Point C is always a point that you need to identify with any graph, the point at which the reaction stops. So, at point C, gradient is 0 because graph is horizontal. Reaction stopped because your limiting reagent is used up. Okay, so how do we then draw graphs for rate of reaction? There are three things that you consider. Okay, number 1, where you start the graph. 2, where you end off for the graph. And of course, your gradient. Okay, the gradient of the graph Okay, so let's look at this question. Effect of temperature. So, say this is your original plot. Okay. If I were to increase the temperature, the volume of gas at the start should still be 0. Okay, because at the start there's no gas. So, but we know that at higher temperature, rate of reaction should be faster. Faster rate of reaction. Okay, because they move faster, collide more frequently, greater frequency of effective collision, so faster rate of reaction. Okay, so higher temperature should be faster rate of reaction, which should tells me that the gradient should be steeper, and it is represented here. Okay, when you see that the starting gradient as compared to the original is steeper. Not just that, can you see that it ends earlier? Okay, it plateaus earlier. Okay, reaction stop earlier. But the total volume of gas evolved should be the same. Why? Now, the total volume of gas evolved is dependent on the number of moles of your limiting reactant. So if the number of moles of limiting reactant doesn't change, where you end off doesn't change. Okay, so where you end off, this one must look at number of moles of limiting reactant. Okay, I say again. Rate of reaction affects the gradient. Okay, so you know increase in temperature makes the gradient steeper. So that's why you at the start, you start at 0 also, because at the start no gas. Then it goes steeper, and then it ends off at the same point, because increasing temperature doesn't increase the number of moles of limiting reactant. Okay, then we look at if it's at a lower temperature. Lower temperature, I know that it should be slower rate of reaction. Slower means gradient is gentler. So that's why, as compared to your original, it has a gentler gradient, and we can see that it will plateau off later. Okay, so the reaction stops later, but it will still end at the same point, because number of moles of limiting reactant did not change. Okay, so let's look at if it's a mass. Okay, let me write at the side. 3 points to think of. Where I start, the gradient of the curve, where you end. Okay, gradient, this looks at the rate of reaction. But where you end looks at number of moles of limiting reactant. Okay, so let's look at the original graph. Original is the line in the middle. If you were to have a higher temperature, this means faster rate, which means steeper gradient. So that's why at the start, you can see that it has a steeper gradient as compared to the original. Okay, so steeper gradient, it should reach the reaction should stop earlier. Reaction stop earlier. Okay, but again, it plateaus at the same point. No change in number of moles of limiting reactant. Now, when you are at a lower temperature, it means this is slower, means the graph is gentler. So as compared to the original, this is a gentler gradient right from the start. It will end, the reaction will stop later. Okay, reaction stop later, but again, no change in number of moles of limiting reactant. Let's look at concentration. This is the one that's more confusing. So this is where your limiting reactant or excess reactant comes into play. If you increase the concentration of excess reactant, okay, say I use the blue one, increase concentration, this means that rate is faster, which means that gradient steeper. Okay, I should still start from 0 because at the start there's no gas, but I know that the gradient here must be steeper. Okay, now how I end though? If I increase the number of moles of excess reactant, this means there's no change in number of moles of limiting reactant. Okay, it's not what limits me from making more product. So how much product I make in the end will still be limited by that other reactant. Okay, so I should end at the end at same point. Same total volume of gas. Same. Okay, but if I were to, so let me just label this is higher concentration. If I were to reduce the concentration, then it's opposite lah, right? Rate will be slower, so graph is gentler at the start. Okay, and it will plateau later, but it will also end at the same point because there's no change in number of moles of limiting reactant, even if I reduce the concentration of the excess. If I look at the mass, it's the same. When I increase concentration, I will have a steeper gradient at the start. Start at the same point, and I should plateau off earlier. Okay, higher concentration, but again end at the same point. Because the same amount of gas is evolved. If I were to reduce the concentration, I start again at the same point, but gentler. Okay, like so. Lower concentration. The more interesting question is here, where we increase the concentration of my limiting reagent. Okay, so again, three things. If I were to increase the concentration of my limiting reagent, first, concentration increase, right? So rate of reaction increase, my graph will be steeper. But because now there is an increase in number of moles of my limiting reagent, this means there is an increase in number of moles of my gas produced. Okay, so that means that I must end more products. Okay, so I can't end at the same point. Okay, so this is higher concentration. Similarly, if I were to reduce the concentration of my already limiting reactant, I will start with a gentler graph, right? Gentler gradient. And I must also less product. Okay, form. Okay, understand? As compared to the original. Effect of pressure is the same as concentration. In this case, we want to see that when pressure increase, okay, it depends on how you increase pressure lah. We assume that you increase pressure by reducing volume of container. If you increase pressure by adding more number of moles of reacting particles, then it goes to this, is it limiting or not limiting? Okay, but we simplify it. We assume that you increase pressure by decreasing volume of container. Okay, so we didn't change the number of moles of anything. Hence, if you were to increase pressure, they are closer together, they react faster, collide more frequently, higher pressure. Okay, and at same point, because no change in number of moles of limiting reactant. If I were to reduce the pressure, you start out gentler and then the two at the same point, because again, no change. Lower pressure. Okay, what about particle size then? Again, when I change particle size, no change in number of moles. You just take something that's bigger and you grind out to more powdery. So technically the total mass is the same. There's no change in number of moles. Okay, so with that, let's look at if I have a larger surface area with the same volume. Increase surface area or reduce particle size. Same thing. It should again end at the same point. Steeper at the start because faster rate of reaction, but end at the same point cause no change in number of moles of limiting reactant. If I were to increase the surface area, then this will be the if I were to reduce the surface area or by increasing particle size, I have a gentler gradient, but I will still end at the same point because there's no change in number of moles of the limiting reagent. If I were to draw the change in mass, it should start at the same point still. Okay, then draw the line. So faster rate of reaction, end earlier, but end at the same point. So this is what? Increase surface area. And this is decrease surface area. Okay, so that's it for how to draw these graphs. Now you may wonder, how come for this question, right? I say increase the concentration of limiting reactants or decrease, but I didn't have a mass graph. That's because when you change the concentration of the limiting reactant, the mass would likely change as well, and you don't know what's the change. So unlikely to come out in the question. Okay, so generally speaking, you can see that most of the graphs are similar. They should all end off at the same point unless you have changed the concentration of your limiting reactant. Okay, once the concentration of limiting reactant is changed, you are changing the total number of moles of products that can be formed, and that will change the ending point of where your graph will plateau, okay, of where your graph will flatten to.